Thanks. Yeah, so hi. So this talk is about our paper, Zero Shot Words and Disambiguation using Sense Definition Embeddings. I'm Sawan and I'm from IIC Bangalore, as are Sharmistha and Partha. And Karan is at CMU. So to briefly introduce the task, Words and Disambiguation, or WSD, takes as input a word such as tie in this example and its context, such as he wore a vest and tie, and tries to predict the right sense. And typically it is assumed that the candidate senses for the word are known a priori. In the next few slides, I'll go through some of the existing approaches which are used for building WSD systems. So first up are supervised systems, which need sense annotated training examples. They typically perform best on the standardized test sets which are there for WSD. However, an obvious issue is that they cannot handle unseen words and unseen senses. For example, if you consider this example where the word tie and two of its senses are seen while the word vest and the other senses are not seen, not much can be done using a supervised system for the unseen words and unseen senses. So to solve some of these issues, other methods are used which use external knowledge. For example, one set of methods uses context definition overlap heuristics. The idea is that the context in which a particular sense occurs has some overlap with the definition of the particular sense. So these methods can handle unseen words and unseen senses, but the overall performance remains worse than the supervised systems. Another set of methods uses knowledge-based approaches which use lexical knowledge bases. For example, WordNet has this set of relations which connect the different senses of different words. For example, we have a necktie is kind of a neckwear and a Windsor tie is a kind of a tie. Using this information, we can disambiguate words in a sentence through a coherence measure which can be built across the different candidate senses of each word. For example, in this case, the vest 2 sense of vest and tie 1 sense of tie have something in common in the LKB, in the knowledge base, which reinforces, we can build some weights on them and build a model using that. These models can handle unseen words and unseen senses, but again, the performance typically is worse than the supervised systems when you compute the overall performance. So far, we have seen 3 kinds of methods: supervised and definition-based and knowledge-based. We saw in supervised methods that it cannot handle unseen words and unseen senses, while the other 2 can handle unseen words and unseen senses, but they cannot use a training corpus. So obvious questions to ask are, can we efficiently leverage external knowledge for supervised systems? And a related question to ask is, how can we make supervised systems handle unseen words and unseen senses? So we propose EWISE, which is a neural WSD model exploiting a combination of data sources, including sense annotation, sense definitions, and structural knowledge. This enables zero-shot learning, and it can handle unseen words and unseen senses. So this is a summary of the last few slides. So to introduce our model, we have 3 major components. On the left, we have the context encoder, which encodes a natural language text which contains the word to be disambiguated. On the right, we have a definition encoder. And on the bottom right, there's a knowledge graph embedding, which is used to learn the parameters of the definition encoder. I'll get into the details of each one of these modules. So to begin with, we have on the left a context encoder, which takes a natural language sentence which has, say, tie as the word to be disambiguated. It is fed to a bi-LSTM, followed by a self-attention module, which outputs a representation for each word in its context. We then compute similarity of this representation to each candidate senses representation. And the way we obtain this candidate sense representation here in this table is through a definition encoder, which I'll describe in the next few slides. Before I get into the definition encoder, we use knowledge graph embedding, so I'll briefly describe how these work. In WordNet, we have this lexical knowledge base wherein, as I said before, we have the connections between different things of different words. For example, hyponymy and hyponymy here. In the terminology of knowledge graph embeddings, the senses are called entities and the relations are called relations. So a typical knowledge graph embedding method takes this as input and converts it to an embedding space wherein the senses as well as the relations will be mapped to a vector space in a meaningful way. So the way we learn a definition encoder in our case is we begin with the knowledge base in WordNet. Okay, this is supposed to be a relation here, which is a hypernym. Somehow it got changed. So we begin with a knowledge graph, and we learn the parameters of a knowledge graph. We then replace the entity, which is a sense here, through encoding of its definition. So a sense is now represented using an encoding of its definition, and the encoding model is basically a by LSTM, and we do a max pooling over that. So in this way, we capture the information in the lexical knowledge base in the definition encoder. At inference time, we do not use the knowledge graph embedding part, and we simply use the encoding of a definition to generate the sense embedding. I'll now go to the results. So we take one model from each representative kind which I described before. To begin with, the first, WordNet S1 is the most frequent sense baseline. Less extended is a context definition overlap-based method. Babel5 is a knowledge-based method. HCAN and ByLSTMA are supervised methods. ByLSTMA is basically ByLSTM with attention, which is an ablated version of EWISE, which is our method. So first up, we compare with some baselines, and we find that EWISE improves on state-of-the-art. While this was not the goal of our approach, it's useful to know that it still improves the overall performance. Before I go further, I will describe a back-off approach which is used in the previous supervised methods, wherein when a word which is not seen, for example, west in this example, we use a back-off method. So if tie is a word which has been seen, we use a learnt model and predict using the word in the context. If a word is not seen, such as west, we use a back-off which basically looks at a sense frequency table and picks for that particular word the most frequently occurring sense. Next, we compare our performance on rare words. So we basically split the test examples into different frequencies of 100 examples. So on the x-axis, we have the number of times a particular word occurs in the training corpus. Here we see that with our system, we get gains for frequent as well as rare words. Specifically for unseen words, which is the first category here, we do better than the knowledge-based approaches. In this next slide, we compare performance on the rare senses, which is the outputs of a WSD system. So here we split the examples into two parts. The first is the examples wherein the right sense is the most frequent sense, and the other set, LFS, is all the other examples. So whenever the right sense is not the most frequent sense, it's part of the LFS set here. Here we see that while the performance on the most frequent senses is comparable and similar, we get improvements on the LFS set significantly. The next slide, we do an ablation study using our method. So EWISE is our approach. ByLSTMA is an ablated supervised method, and we allow it to have back-off. And next, in the third row, we have ByLSTMA without back-off. So just to reiterate, EWISE does not use any back-off. And we can confirm from here that using sense embeddings as targets, as we have done, is better than using a back-off. Next up, we ask the question, can our method learn from limited data? So we essentially run our model with 50% training data and compare with the existing approaches. So when we compare with the ablated supervised version in ByLSTMA, we find that even with 50% data, EWISE is able to outperform the supervised version. And also, if we compare with the knowledge-based approaches, this shows that with limited data, we are able to improve upon knowledge-based approaches while using the same resources. So essentially, if we compare, the knowledge-based approaches can be seen as an ablated version of our method, wherein training data is not used. And this shows that with small amount of data as well, we are able to learn with EWISE. In summary, we present a principal framework to learn from a combination of data sources, which includes sense annotations, definition of senses, and structural knowledge. We enable zero-shot learning for WSD, that is, we can handle unseen words and unseen senses. There's a GitHub page for this project, and you can contact me on my email. The work was supported by Government of India, MHRD, and a travel grant from Microsoft. Thanks.